Hey, how's it going? So, following up the last video, I want to talk about deductive reasoning. A little bit different from deductive reasoning, or sorry, deductive reasoning. So, we had discussed inductive reasoning, where that's based on just making an observation, while deductive reasoning is the process of proving an observation. That's where it differs. I write down the definition given in the chapter here, so I am following from the textbook. Is as such, I just saw a picture from. So yeah, following from the textbook. We'll do where I mean, I'm not going to specifically read you the textbook, but I will be following through the textbook. It's specified in the college semester. All right, so deductive reasoning. Take this to be a definition here, and that is the process of proving a specific conclusion from one or more general statements. Conclusion based on one or more general statements. Sorry. So if you have some conjectures made, some observations made, and so deductive reasoning would be actual proving of that. So if a conclusion proven to be true by deductive reasoning is called a theorem. Called a theorem. And you've probably heard that word before, everyone knows the Pythagorean theorem. I think they just discussed that the sum of the squares of two sides of a right triangle, a third side, blah, blah, blah. But so, all right, so that's called a theorem. It's something that you've proven to be true, and proof comes with a given certainty. It's not what people may call proof in the everyday sense. Proof has an absolute certainty. If you can correctly prove something true, there's absolutely no doubt about it. All right, so there are some specific examples here given in the text. I'd encourage you to read through those. But I want to discuss what they give in example 5. So consider the following procedure. Here's an interesting example of an everyday thing where we can make some hypothesis and prove it to be true, and in fact prove a theorem. All right, so what do you do? One, select a number, any number. Select any counting number, I'm going to say. Number, 1, 2, 3, 4, and so on. Just positive integer numbers we'll take this to be. All right, and then 2, multiply by 6. Multiply it by 6. 3. Add 8 to the previous number. 4. Divide the previous number by 2. Number by 2. And I'll clarify this. We'll go through some examples to make sense. So, and then a fifth step we're going to take, subtract 4 from the previous number. All right, so what can we say about the resulting number? All right, so first let's make some observations. All right, so we'll do 1. I'm going to choose a number. How about a 3? All right, so to clarify this process I've specified above. And then 2, what do I get? I multiply it by 6, so 3 times 6 is going to be 18, I believe. And then 3, you're going to add 8 to the previous number. 18 plus 8 is equal to 26, I think. And then 4, I was to divide the previous number by 2. 26 over 2 is 13. Okay, and then 5, I get 13 plus, no, I'm sorry, 13 minus 4. And that is equal to 9. Alright, so what can I say? It looks like maybe that's 3 times the preceding number. Let's do another example. Alright, so I'm going to take any number. I'm going to take a number that's maybe not so big. I don't know, we'll take, I don't know, any number. 8. Why not 8? Okay, so then in 2, what do? I do 8 times 6, and that is 48. So I'm going to multiply the number by 6. That's our arbitrarily chosen number, counting number. And then add 8 to the previous number. 48 plus 8, well, that is 56, I think. Right. Add 8 to the previous number. Divide the previous number by 2. For 56 over 2. And interestingly, this is always going to be a whole number when you do divide that by 2, because I've multiplied by 6, and that'll always be a factor of that. One observation to make, but not really the observation we're after. But this will always be an even number, so it'll always produce a counting number. That is going to be 28? Is it? Yeah, 28, I think. Calculator if you need to, but all right, so 28 and then 5. What am I going to do here? I'm going to subtract 4. 28 minus 4 is equal to 24. So observations here. All right, so we had 3 times 3 is equal to 9, and 8 times 3 is equal to 24. So let me make a conjecture here. This procedure always produces 3 times the original number. Times the original counting number. All right. Oh, I'm sorry, that looks so scribbly. 3 times the original counting number. Could this be so? And can we prove this? All right, so could this be true? Well, I mean, possibly. We've seen 2 examples. Yeah. Worked for 2 examples. However, there's infinitely many, so it doesn't prove it. Proven. Not proven. No, sorry. Since infinitely many possibilities. Sorry. So scribbly there. All right, so however, all right, so take n as a general number. That's a variable. I've probably seen variables in math before, if not. So n can just be any number that we want. And then what do we get? So we get 1. Our number was, so that was, as our step-by-step process above. We'll just start with the general n and see what happens. In 2, we get 6n. All right, I was to multiply the number by 6. Okay. 3, then I was going to add 8. So we get 6n plus 8. Okay, and then 4, I was going to divide the previous number by 2. So 6n plus 8 over 2. And I can write this as 6n over 2 plus 8 over 2. Be careful. I mean, I can separate within the numerator, but not the denominator, right? So, and then what do I get? I get 3n plus 4. And then 5, I take 3n plus 4. Let me put some parentheses to be clear there. That was my previous number. And I subtract 4. And lo and behold, what do I get? I get 3n. All right, so we see that for any n, the procedure produces 3n. In fact, it doesn't even need to be a counting number. You could say if any real number, I mean, you get rationals and irrationals, whatever, but the procedure did in fact do that. So we can state this as a theorem. Thus, we can state this, the conjecture, as a theorem. And that is to say there's a theorem. The 5-step procedure described above, above produces 3 times the original counting number. And notice that some clarity was added in using a variable rather than the specific example. Well, oftentimes, especially when students are, new to these ideas, they're very troubled, like by working in a symbol. To me, it's easier just to work in the symbol. I didn't have to make any of those calculations. But that's not the point here. We're not going to go too far with trying to prove theorems in this course. It's just more a general idea of deductive versus inductive reasoning. So, read through this section of the text. It'll be helpful. I don't think we'll be tested on this part, but these are important foundational things. We'll spend a little bit more time discussing the first chapter before moving on to chapter 2, which is more in the core stuff that we have to cover and be tested on for this course. All right, we'll talk to you again soon.